Hey guys, thanks for bearing with me during this coronavirus edition of Gears and Gadgets, being brought to you from my studio personally. Um, I hope this is an adequate substitute for what I'd like to teach you guys in person. At least if anything, you get a little behind the scenes peek as to what I do in here a little bit, maybe. See some of my crap. Keep all my crap well organized and all over the place. So, I guess we should get on with it. So these are light emitting diodes. They come in all sorts of colors, shapes, sizes. This one's ultraviolet, some are infrared, some come on strips, all sorts of shapes and sizes, all run on DC power, and you can use them in all sorts of different ways. One of the things to remember is that they are polarized. There is a positive and a negative side of the LED. Putting it in reverse won't necessarily damage it, but it certainly won't work. Every LED you go out and purchase is rated with a forward voltage and a forward current, meaning the maximum limits at which you can run that particular LED. You can go slightly below on voltage, but meeting and the exact voltage is the best way to work with it. Forward current, it will draw itself, and you can limit that current with resistors, which we will be talking about next. Always protect your LEDs with resistors because they are very delicate to lots of current. The schematic symbol at the bottom there, that is how you would see an LED represented in an electrical schematic if you were to Google it online. There's a positive side and a negative side, and it'll only work in that one direction. The voltages vary from color to color, from type to type. If you don't buy it and you find it, to figure out the voltage, start low and then just give it a little bit more and a little bit more until you find the voltage that it'll light up with. And you've found the forward voltage. So earlier I mentioned that LEDs are polarized, meaning there's a positive side and a negative side, meaning one side should be towards the positive side of the battery and the other side towards the negative end of the battery. In your classic LED that you would buy out of the store, it sort of has a bulbous type shape, a nice round top, and it'll have two legs. A short leg, that's negative, and a long leg, that's positive. If these legs are cut, let's say you scrapped it out of a different object, you can look at it from the top. If you see this rim around the LED, at the leg that is the negative leg, there will be a flat sort of ground into that side of the LED, and that leg that's towards the flat side will be the negative leg. If you have an LED that's not round and has its legs cut off, all you can do is experiment and pray. But those are the general guidelines for figuring out which polarity works. So resistors literally resist. They impede the flow of electrical current. It's measured in a rating called ohms, which is the omega sign. And the more resistance you add to a circuit, the lower the amperage flowing through that circuit. The reason these are going to be important for us right now is that resistors we use to protect our LEDs from too much current. More resistance, less current. We need low current for our LEDs, so we'll be using resistors to restrict the current and the flow of power to the LED. They come in all sorts of different sizes. The size means almost nothing to the amount of ohms. Mostly it has to do with the watts that it can take, the amount of power it can take before overheating. Starting from the top to bottom, the 33,000 ohm resistor looks a lot like the 3,300 ohm, and a lot smaller than the one that is actually higher than both of them, the 47,000 ohm. So learning to read their colors is important with this normal type of ceramic resistor. These larger types of resistors are usually printed onto them, 1 ohm, zero point 0.1 ohm, and then these fancy ones, which I'll talk about in a simple circuit later, these are resistors that vary with the amount of light that makes contact with them. So this one can be as low as 5,000 ohms and as high as 250,000 ohms. When you read a resistor, you want to hold it where the gold or silver line is on the right. That's your tolerance stripe. It tells you the tolerance of the resistor, meaning plus or minus 5% if it's gold, 10% if it's silver. Not usually a huge factor for you, especially right now. There's always 4 stripes. The first 3 indicate numbers. They're using colors as numbers, and each color, dependent upon where they are, means a different type of number. The same number, but it uses it in different ways. So the first one here is the number 4, yellow, followed by an orange, which stands in for 3. Red in the third line, usually in any other line, means 2, but because it's in the third line, it's asking us to essentially add 2 zeros to that number. So reading this across is a 4300 resistor, which is a 4,300 ohm resistor. So that's how you would read a resistor like that. We'll talk about the colors in just a second. So as I was saying before, when you read a resistor, you're looking at colors to determine numbers. And where in that line of stripes the color appears determines what that number means. So if you're looking at any of the colors in the first 2 stripes, they actually stand literally for the number that they stand for. 1, 2, 3, 4. So if it's a red-orange, first 2 colors, that's a 2, 3. So we know it's a 23 something resistor. The third stripe is what determines the multiplier of that color. So the red is 2, which essentially means you add 2 zeros. If it were brown, you would just add 1 zero. So it would be, if a red, orange, brown resistor would be a 230, 230 ohm resistor. Works that way across the board. The only weird part is black in the third stripe. Essentially, you move the decimal place to the left 1 position. So if it was a red, orange, black resistor, that would be 23.0. Wait a minute, that would actually be a 2.3 resistor. Everything else follows a pretty simple pattern, and if you kind of notice, it's brown or black-brown, Roy G. Biv, for those of you that remember colors like the rainbow, ending with white being 9. So this holds true for any and all of the colors. Just watch which stripe it's in. The third stripe determines your multiplier. Gold and silver are just your tolerances. Don't worry about them at this point. We're also going to be dealing with one other type of resistor, and those are potentiometers. They're variable resistors. They're resistors that can change how much resistance they give you depending on how you hook up to them. They have 3 pins coming out of them, unlike the other resistors, which you noticed only had 2. And they come in, again, a variety of sizes and shapes that mean almost nothing when you actually look at their total resistances. The biggest one here is actually not the largest one of maximum resistance. That's this guy down here, which is actually fairly small. So always check to see how much the variable resistance is. It's always labeled with the maximum amount of ohms. So it can go from that number, 1 million ohms, which is 1 mega ohm, to 0. So that's the range. It's labeled with its maximum, but it can also go all the way down to 0. The same thing with any of these other types. I'm also labeling them longhand and shorthand. So This is 1 million, but if you see it written out, you'll most likely see 1M and then the ohm sign. Just as you would see 50K, the ohm sign. It works a lot like money in that way. All of these types of things, if we take a look at them, they all have knobs that rotate, little knobs. This one's pretty easy to grab, something like this you'd find in a stereo. Other ones like these types you might find in smaller electrical devices, the volume knob on old style CD players, Walkmen, all different sizes, all different types of resistances, but on the inside they all look the same. There's a ring essentially of resistive material going from one lead to the other. All resistance. Essentially it's the same material that's inside the other resistors. The third pin to the potentiometer is where you hook up your voltage to vary it with this wiper that lives on top of this rail. So as you travel from one side to the other, you're literally putting less resistive material or more resistive material between your contact point and the other contact point. So what this means is that if I hook them up to these two, I can vary my resistance, no problem. If I hook them up to these two, I can vary my resistance. It'll work in the opposite direction. But if I hook my leads up to these two, I will be getting the full resistance of this particular potentiometer because I'm not hooking up to the varying part of the variable resistor. So here's an example of the simplest circuit. The simplest circuit in both a schematic and in a sort of practical real-life situation. So if we look at the schematic, all schematics have a positive and a negative point. The electricity always needs to come from one and go to the other. You can say conventionally electricity flows positive to negative, but in particle physics it actually goes the other direction. Don't worry about that. Just think of it as going from positive to negative. And in this circuit, meaning a circuit from positive to negative, that's all a circuit is, we have a resistor and an LED. Now the resistor is there so that we do not provide too much current to our LED, and the LED is there to be the thing that's actually doing something useful. Any load between positive and negative is technically okay. We could remove the LED and it would be a valid circuit, but it wouldn't do us much good. Over here, we've got two AA batteries, and these AA batteries are lined up in series in this particular case, which means both of these 1.5 volt batteries are combining to provide me 3 volts to my LED in my circuit. I have a tiny little 330 ohm resistor here and an LED that wants just about 3 volts. So I'm just going to touch them together and complete the circuit. Simple as that. All of this is just taped down. There's no soldering involved right now. Simple. And inadvertently here, we've made ourselves a little touch switch. You know, this is as simple as it can be. You can get really creative with the ways you interact with your electronics. The simplest of circuits. So now we're going to work with these components in a practical application in a way that you'll be able to do when you get your kits in the mail. Right now I've got 2 AA batteries, again in series, making a 3 volt circuit. I have that hooked into my breadboard. This breadboard, this is a means by which we're going to be able to prototype and figure out circuits without actually having to do any soldering whatsoever. The components of the breadboard operate like this. We have these long columns on either side of the breadboard, and each one of these dots is connected to each other one of these dots. This outside lane is separate from the inside lane, but every connection in that lane is connected to each other on both sides of the board. What I've done here with these 2 wires is connect the outside to the outside and the inside to the inside so that when I provide power to either one of them, I'm getting power everywhere. So as I construct my circuit, I don't have to choose which side to go to retrieve my power. I have options on both sides. Now that I have my batteries plugged in to my long rows, I can start to work with these smaller sections. They all have numbers so I can keep track. All of these are only connected top to bottom in this orientation. So let's say row 8 is connected to every other dot in row 8 and only that row. They also do not jump this center gap and continue on. So number 8 here is separate from number 8 here. And knowing this, we can start to manipulate where our power is going and to which appliances they're going to. I'm going to use a handy dandy LED. Looking at its legs, I'm going to know that this one is the short one and that's the negative side. I could also look for the flat that's on the LED, and it is on that side. So I'm going to make sure that my flat, my negative leg, is plugged into the negative side of one of these rails. Doesn't matter which one. And then I'm going to bring it out into the smaller columns here. I'm going to take this opportunity to play with a light-dependent resistor. Connect that from the same row as the other leg of the LED to the positive side of the battery on the other side. And there we go, it lights right up. The beauty of this particular type of resistor is that by varying the light, I can vary the amount of power going to the LED. So it can almost act as a small switch. It'll act as a sensor with a microcontroller like an Arduino. But it's a way that we can start to get slightly more fancy with how we're using our light. I wonder if you guys can even see that. I guess you can kind of see that getting dimmer and brighter. I'm going to shut the lights off in the studio so that you can get a slightly better look. You can see it's very dim right now, but with this flashlight, I can start to increase the amount of power flowing through it to a pretty large extent. So that's the interesting power of light-dependent resistors. They can make interestingly interactive circuits. So that covers the basics of DC circuit making and most of the appliances and equipment we'll be using from the get-go. If you guys have any problems, don't hesitate to email me and order your Arduino kits so that next week we can get started with those. I'll make another video that should hopefully help you guys through the process. Be safe, stay healthy.